Hey folks, today I'm going to be recording a quick demo about a CRDT project called automerge. This has kind of been around for a few years and there's a number of contributors around it, but it is quite interesting. I'm going to show briefly the docs and things, but you can read about it yourself, and then I'll show some experiments that I was doing with it this weekend. Yeah, it is an interesting project because we know about CRDTs in general, but this is a kind of a good library, solid core library with some opinionated systems about not only how to represent the CRDT and what the nodes in a graph look like, but also how you merge those together, how you persist on disk, how you track changes in a kind of Git-like format. And yeah, how you kind of synchronize two different processes together on the same view of what you call a document. So briefly to touch on some interesting concepts here. Document is the core thing that you're looking at. It has a kind of tree-like structure, and the things in the tree are kind of like JSON data types. There's counters, numbers, maps, lists, and those. The interesting thing here about this project is that those node types, let's see if we've got, here we go, like simple values. These node types determine how they are merged together and how conflicts are resolved, which is nice because usually it's the kind of thing that becomes a business, like it's part of your business logic. But here it's tracked on a very granular level, and so you can reason about how larger objects are merged based on the data types of the nodes within them. So it talks about how it resolves conflicts based on like sequence numbers and the like who was last working or who last changed value somewhere. By who I mean like the actor. Yeah, and counter is probably a good place to start because here it's like it's an integer type, but we are annotating it with this data that it is a counter, which means that we can do this kind of global aggregation of values to it, and it knows how to track increments and decrements separately from one another and how to kind of pull those all together. I think one of the most interesting things about this project is that it doesn't only talk about the snapshot of what a document looks like and how it's merged, but also a lot of the power comes from, and even the way you can make this work at all is that this document is not a snapshot, it's rather the entire history of the document, and each thing is like a commit, which means when you take two versions of the same document, you can find out where they kind of come together, where their common history is, and then you can reason about how to merge any subsequent changes on top of that. So that's kind of all I wanted to talk about here. I think it's quite nice that it's distributed as a JavaScript and a Rust implementation, and so for Golang, which is my kind of language of choice for getting up and running quickly, we instead have Go with like some C bindings that call into the Rust implementation. And so that's what I'm using in the IDE behind here. So I've done kind of 4 experiments here. First one was relatively straightforward. We create a new document and we set 2 different values in it together. We print out the result, we do a commit, we look at what the changes are and create a new doc and apply all of the changes to the new doc and show that they both come out kind of looking the same. So this is just dealing with the kind of the snapshot here, and you can see that I committed X and Y has a map, and kind of, yeah, you get the same document at the end. But silly, just me learning the interface, really. Now, experiment 2 is more interesting, because here we looked at what the sync system is. Now, automerge provides, instead of you having to invent a way to synchronize these docs together, it provides that. And the sync state is basically a way of tracking which, out of two peers, who's got which changes and which ones need to be sent back and forth. So here I create two documents. Each one has a sync state associated with it. And we sync it by, for each, we're doing this just in process, so we don't have to do anything too bad, but we just, for each doc, we generate all messages from it and receive them in the other sync state, and do the same in the opposite direction. So this is like how you sync without any network in the way. So we're gonna we do a sync, but it's an empty document. We show that they have the same view of the world. In this case, there's no changes, so they've got no head commit. Then we do some changes, like we set x to 1, increment a counter, set x to 2, increment a different counter, or increment the same other counter again, and then show that these two documents have diverged. And then we show the head of the first doc, and then we call sync, and then we show that both documents have kind of come back together again. Cool. So this is more interesting because we can show, like, here there's these two maps have kind of diverged, and merging them together might not be trivial, especially if these are deeply nested structures and things like that. And you can see that when it sends, like we're logging the messages sent and received between the structs and the sync state, you can see that it's each time it's broadcasting, like, here's a change, here's like what I think is the head of the document, and here's some changes you might need, and kind of gossips those changes to one another until they all come up to date. And so by the end of it, you can see after the sync, both docs contain the same data. X is 2 and Y is also 2, the counter. Yeah, so then obviously the question comes, how do you, if you actually make a real application with this, how do you synchronize the server and network? Now, the automerge project has some, the merge rules is quite interesting to look at, has some like built-in examples of WebSocket communication for the JavaScript library, and some built-in like sync server stuff. But here we're using Go, so like can't really use any of this. So I did two different experiments. The first was a client and a server, in this, and a database. So in this case, we had a server that has three different APIs on it. First is to kind of create a new document. And then there's an API to retrieve the entire state of the document, and then there's a sync API. And the sync API is not a WebSocket, it's just a single API that uses a kind of cookie idea to track the sync state of the relationship. So the client calls in with no messages and no cookie, and just goes, hey, let's start a sync, and then it gets a sync state back in the cookie, and then each time it requests, it kind of generates a bunch of messages, sends them along with the cookie. The server loads the doc, applies the sync state to the doc, and then applies the messages, and then generates any messages to go back, and then re-renders the cookie onto the HTTP response and sends it back. This kind of worked. Like, if I run it here, and it's going to create a kind of dummy database here with a store and some snapshots and things. Which one is a database? This one here. It's got stores and snapshots, and if I run the client, Now the client's going to do the work of creating the initial state and then starting to incrementally sync. And then it's incrementing a counter randomly every few seconds. So you can see it's doing a sync every second, and then every few seconds it's incrementing this counter. And on the server side, we can see it receiving these kind of WebSockets requests and persisting the doc into the Postgres database. So we can look at the doc. You'll see it points at the latest snapshot, which is changing every now and then. And the snapshot contains the content of the document. Now, it appears to work, and if you run, you can kind of run the client multiple times. And see the next one starts off from the synced state, and it starts contributing counter values. And you see this counter is now going up slightly faster. And we can kind of stop one of these clients and start it again. It'll pick up and start contributing counts. But the sync kind of didn't, and I can stop the server and I can start it again. And it generally works, but I found that it sometimes kind of freezes up. And you can see I've started the server again. These two clients are counting locally, and they say they're syncing, but they're not actually seeing each other's changes. And the server itself is stuck on a view of the document. And this seems to be because it seems to be what happens when sync messages are lost or aren't generated correctly. Means that it doesn't quite know how to communicate the full graph of changes over the network. And if you're missing one of those messages, it just fails to kind of converge. So the REST API wasn't really a useful way of looking at it. And then, so I decided to go to a kind of WebSocket procedure. As you can see, the sync procedure that you saw with sending and receiving messages is ideal for WebSocket because it's bidirectional communication continuously. Messages are sent in response to other messages in both directions. So WebSocket was the better way to do it. So that's what we did. We got a bit of a neater program here. This time the server also has a Postgres database, or no, sorry, SQLite database. I'm using SQLite. And two APIs. One gets the latest state of the document, and the other is the WebSocket sync API. This time, there's also there's two Go routines here. One is running the web server, and then there's another one that every now and then backs up the cached version of the automerge document that's in memory, backs it up to the database every 5 seconds. So that's just, I could back it up like more frequently when stuff has synced, but it's just easier to have an incremental backup procedure here. Cool. So the sync API is now much simpler because now we upgrade the connection into WebSocket and we call a sync method. And the sync method runs two Go routines. The one that reads messages off the channel, puts them into the sync state, and the other generates messages from the sync state and puts them onto the channel. And the server and the client both do the same thing. So the client is also simpler now. It loads the latest content, builds a document from that, and then starts two Go routines. One that continuously attempts to connect and sync. If it disconnects, it tries to reconnect. And another Go routine that increments a counter randomly. And so this demo is a bit more fully featured. We can start this one as well. And there's some warnings because actually let me I'm going to start a number of clients, so let's find my run configurations. Cool. So there's some warnings here because I've imported GraphViz as a way to render the graph. You'll see that later. But so the server just starts up, ensures initial tables exist. I think it creates an initial document as well. And now we can run one of our clients. Cool. So you can see it established the base document with no content, and it's incrementing. Now there's no like explicit sync requests because we opened a WebSocket and there's messages going back and forth in the background. But you can see this counter slowly going up. And you can see on the server side that we're backing it up every now and then to our data store. So we can run multiple copies of our client. Let's start 3 different copies. They're all going to have different all going to have different actor IDs, and the IDs being a pain here. I don't want to rerun it. I need to allow multiple instances. There we go. Cool. Cool. So now we've got 3 different clients that are all attempting to increment the counter, and you can see that it's jumping up by more than 1 because other clients are also incrementing the counter at the same time. Right, so we've had these 3 incrementing the counter for a while, and the server's been doing its job, so we can kind of stop them and take a look at what the resulting document looks like. Let's close it there. You can see each one is doing a dump, and it's dumping its own an SVG that represents the graph of changes. So we can look at server still running, but we can look at what these SVGs look like. This is rendered with GraphViz. There we go, scrolling. So you can see that we start with 1. So each of these is a diff, like a change ID hash, and the agent sequence number and the value of the counter. So this client ran first by itself, incremented 11 times, and now you can see it started to see changes coming in from other clients. And you can see each time both clients are incrementing, and then one of them kind of merges the changes together, and then they're kind of incrementing together here, and each time kind of coming up to an aggregate count. So for example, we had 21, they both incremented it, they're kind of tracking additional changes and then emerging at 25, because we had 21, 22, 23, 24, and 25 as the resulting count. And then we introduced a 3rd client. Things got even more messy here, and then we shut them down, and then that original client remained kind of the only one committing. So that's kind of, now with a global counter like we've got here, these merge operations are very trivial, but the benefit of automerge is that these documents that we're merging could be quite complex JSON documents, and so there's a whole structure here about how do you model data, how many documents to use, what's the structure of those documents, how you merge things. If you go through all the conflict stuff and the like, it's very interesting as to how you should merge things. For example, like how you, instead of having deeply nested things, you prefer to like denormalize things into a more columnar format and the like. But yeah, that's kind of what I wanted to demo was a set of counters, a distributed counter, and with a database that we can kind of shut down, and the clients can carry on counting, and we can start the database up again and run it. And so off the back of this automerge library, you can build a lot of kind of client-first systems where they hold the bulk of the state on the client side, and there's a server that kind of you can use as a peer-to-peer kind of synchronizer, or the like source of truth with backup. So yeah, I'm going to keep using this a bit and hopefully build a small application on it in the future. But yeah, good fun.